Okay. All right. So, today we are looking at how to evaluate definite integrals. And definite integrals are going to be the ones that have the limits on them. So, we have already talked about what those mean as far as like graphs go, right? So, that means like the area underneath the curve from whatever the first limit is to the second limit. So, this is like a sort of an alternate definition for the fundamental theorem of calculus. And once again, we are short on time, so I'm not going to go through a big explanation of how this relates to our other fundamental theorem of calculus. The other version of the fundamental theorem of calculus was where we said the derivative of the integral of f of x equal, or f of t dt equals, and then we just get f of x there. So where we're taking derivatives of integrals and they cancel each other out. So in this case, f is a continuous function on the interval from a to b, and capital F is an antiderivative of f. What you guys were doing last night was taking antiderivatives, right? You were doing the opposite of differentiation, right? We increase our exponent by 1, we divide out front by that new exponent. Whenever we have a problem like this, we can evaluate the number from the equation without having to have a graph for these. So let's look at let's think about what it means. I think position, velocity, and acceleration is a really good way to think about what this means, right? So if we think about having a graph for if we think about having a graph for velocity, right, then we'd have something like meters. No, wrong. We'd have seconds down here, and we'd have meters per second here, right? And then we would be finding like the area under the curve from 1 to 4, right? And so whenever we find that, we have already like talked about this, right? That is going to be, we're doing meters per second times seconds, which just gives me meters, right? So this is my change in position for, my pen is not working like it's supposed to, and I don't know what's wrong with it. For t equals 1 to t equals 4. Another word we could use for that is displacement, right? Like how far this is from where it starts. So if we think about this using that fundamental theorem of calculus, right, that we just saw on the last slide, when I integrate velocity, right, if I integrate velocity, then I will get position plus c, technically, right there. So when I integrate velocity, I get position. Let's let position for this one equal x of t for that. So the way that we'll write this a lot of times, when I integrate velocity, I get x of t plus c, right? And then we'll put this like bracket here. We don't put brackets like on both ends most of the time. This bracket, and we'll put a 1 down here and a 4 down here. And then we'll plug 4 into this equation. So we'll have x, nope, there's not a parentheses there. Well, actually, no, I meant to do that. There is. X of 4, it's a 4, plus c, minus x of 1 plus c. That pen not working is so annoying. It's hard to read. Okay, so now let's think about those c's for a minute. I hesitated. I almost did not include the c's because watch what happens with the c's. This is x of 4 plus c, and then the negative has to get distributed right here, right? So I've got minus x of 1 minus c. What's going to happen to my plus c and my minus c? They cancel each other out. That is going to happen every single time on a definite interval, right? So if you have a definite interval, plus c's are not necessary. So you don't, because they're going to cancel each other out every time. So you don't have to use a plus c whenever you're doing a definite interval. If there are not limits here, if you don't have a 1 to 4, if you just have an empty integral sign, then you must have a plus c. So if we think about what we have here, x of 4 is my position at t equals 4. And my x of 1 is my position at t equals 1. Gosh, let me turn my computer off and back on and see if that helps. Alright. So, if you think about that, we already kind of knew what this was supposed to be because we've talked about areas under curves and graphs and units and stuff. So this is supposed to be change in position from t equals 1 to t equals 4. Well, the change in position, the way you could find it is say, well, here's my position at 4. Here's where I was at 1. I could just subtract these two, and that's the difference in those. That's a change in that position, right? So, when we integrate, it gives us the change in the function that's sort of like the level up from that, right? Whatever you would have whenever you integrate. I'm not going to go through A for the sake of time right there. Let's look at some problems. You could do x of 4 minus x of 1, particularly if you are dealing with just a function like that. I would probably skip it. If you're doing a problem like we see here, we're going to have to actually integrate right here, right? Because we don't have like f of x. We've got an equation that we have to integrate. So on these, I do like to write that step right there. So we've got to integrate 4x squared minus 2, right? So I will increase my exponent by 1, just like we were doing last night, and then divide out front by that new exponent. So I'll have 4/3 x to the third. What do I get when I integrate the 2? 2x. And then I like to put my bracket right here where I've got 0 to 3. You do not need a plus c on definite integrals because plus c is going to cancel out every time. Because you will have a positive plus c here, and you'll have a negative that has to be distributed, and you'll get a negative c here, and they'll cancel out every time. So if you have limits right here, like if you have numbers right here, you do not have to put a plus c. If you do, it's fine because it's just going to cancel out and go away, but you don't need to on those. Yes? The limits right here, if you have numbers right here. So if you do not have numbers right here, then it's just like you were doing last night, and this would be your answer, and you'd put a plus c on the end for those. Okay? So now you need to plug those numbers in, right? So you would do 4/3. You always do the top limit first. So 4/3, 3 cubed minus 2 times 3. And I like to put like an extra set of parentheses or bracket around that first part. So that's what I get when I plug in the 3. And then I'll have minus, and then I'll have 4/3 times 0 to the third minus 2 times 0. And so here, I could cancel this 3, one of those 3s. That'll save me a little bit of time. So I've got 4 times 3 squared. That's 4 times 9. I got 36 minus 6 right here. What do I get in that second set of brackets? That's just 0 right there. So I am going to get 30 for that. Not necessarily on this. I would just do like I've done here, sort of like a string of equal signs showing your work. Alright, 2. I don't know how to integrate that like it is right now, because it's sort of like a chain rule situation, and we have not learned how to deal with that yet. We're going to, but we haven't yet. So, your only option right now is to expand this first. So, for this, we would integrate from 1 to 2. I have not integrated yet. I'm just expanding. For this, we're going to square, double, square, or write it twice. 2x plus 3 times 2x plus 3. So I'll get 4x squared plus, I'm going to multiply 3 times 2 is 6, and double it. I get 12x, and then square the last. And then I can just use my power rule to integrate here. So when I use that power rule, I'm going to increase the exponent by 1. So I've got x to the third, and then I'll have 4/3. And then I'll have x to the second. I'll divide out front by 2, which will give me just 6 here. And then I'll have a plus 9x. And we're going to evaluate this from 1 to 2. So whenever we do that, we're just plugging in 2 and plugging in 1. It'll look like this. 4/3 times 2 to the third plus 6 times 2 squared plus 9. My pen is getting worse. Times 2. So that's where I plugged in my 2. And then I'm going to subtract. Now I need to plug in the bottom limit, which is 1. So I have 4/3, 1 to the third, plus 6 times 1 squared, plus 9 times 1, like that. And because we only have 10 minutes left, we're going to pretend this is an FRQ, and we don't have to simplify when we leave our answer like that. But you would just, simplify that out if it wasn't. I would say this one right here is sort of the upper limit of what you're going to see on calculator inactive. You could see this calculator inactive, but I don't think they'd ask you to do much more than that. Because your arithmetic gets a little extensive here. Probably, or if it's not really an issue because you don't have to simplify this. So they might give it to you on FRQ, but you could just leave this answer I've got right here if it's FRQ. This is sort of the upper limit of what I think you'll see on multiple choice, just because it gets too time consuming and that they're not able to test what they want to test. Okay. All right. We need to know how to take some other derivatives. Okay. I have put over here on the left all of our differentiation rules. our integration rules are just sort of the inverse of that, right? So the derivative of sine is cosine. So if I integrate cosine, I get sine. Now, sines are opposite of what they are for derivatives, so be careful with that. Like, derivative of cosine is negative sine, right? But the integral of cosine is positive sine. So, integral of sine is negative cosine. Those two you've got, like, for sure you're going to see those. Got to know those well. Then, these are less likely to show up. Notice that we can only really integrate secant squared, secant x tangent x, cosecant squared, and cosecant x cotangent x. Like, I can't integrate tangent. I can't. We're going to learn a way to integrate tangent, but it's much more extensive than a memorized rule for that. So you can only really integrate the things that were the answers to your derivatives over here for that. So these need to be memorized. Sine and cosine are so important that they're memorized. You know, the other stuff's not going to show up a ton, but you're going to see it a little. So you need to know those. All right. So if I have a problem like this where I need to integrate sine x over cosine squared x dx, I don't know any quotient rules or anything like that. I only know power rule and the rules that were just on that last slide, right? So there's not like a quotient rule sort of thing that I'm supposed to do here. This must be able to be rewritten as one of those integrals that I can find. Particularly, here's what we can do. Interval from 0 to pi of, I'm going to write this as sine x over cosine x times 1 over cosine x dx. Is that okay? If I multiply that back together, do I get what I started with? Right? What is sine x over cosine x? That is tangent of x. What is 1 over cosine x? Secant of x dx. And whenever we look back at the last slide, what is, now I don't have tangent x, secant x, but I've got secant x, tangent x, same thing, right? The integral of secant x tangent x is secant. So when we integrate this, we are going to get secant. So I will get secant of x, and I need to evaluate that from 0 to pi. Which means that I will have secant of pi minus secant of 0. Secant's 1 over cosine, so it might be better for you to think of 1 over cosine of pi minus 1 over cosine of 0, unit circle. Cosine is your x coordinate there. So we've got 1 over negative 1 minus 1 over 1. That is going to give us negative 1 minus 1. And we get negative 2 for our answer. Okay, questions here? I know we're not going to get to the end of these notes, but I think we can do logs and exponentials for these. So, logs. When we took the derivative of a log, we got 1 over x. So if we integrate 1 over x, we get natural log of, we have to put absolute value bars around the x because you cannot take the log of a negative number, right? Plus c. So if I see something like this, 2 over x, then that could be written, as 2 times 1 over x dx. So that 2 is just a coefficient. I'd have 2 times the natural log of the absolute value of x. This one will have a plus c. Do it in there as a reminder. That one's not a definite interval. I'm not going to do all of 5, but I want to show you how to set up 5. This looks terrible right now, right? But what could I use to break this down so it wouldn't be like quotient rule looking? I could either move that x squared up to the top and make it x to the negative 2 and distribute. Or you may think of it like the love connection right here, although it's going to be a triple love connection right there. So if you do that, you're actually integrating from 1 to 3. You'll just have a 3 because 3x squared over x squared, the x's will cancel. Plus, when I have 5x over x squared, I'm going to get 5 over x. And then I'll have 2 over x squared. But that is not a natural log because the x is raised to a power. I want to write it as 2x to the negative 2. So then you would integrate each one. That middle piece, that 5 over x, is a lot like example 4 right here. You're going to get a natural log in that spot. I don't have time to finish that one there, but you'll integrate like we did for the others. Exponentials. These are the easiest problems. Okay? What is the derivative of e to the x? E to the x. So what is the integral of e to the x? E to the x, right? So if I see something like I've got here for number 6, I would have that 5 right there could really just be like a 1/5 e to the x. So when I integrate the e to the x, I still just get e to the x. And I will evaluate that from negative 2 to 3. So like my answer for this one is going to look like this. 1/5. And then make sure you got a bracket or parentheses here. E to the 3rd minus e to the negative 2. Like that. And that feels like you need to like do something else with it. But it e to the 3rd is a number. That is a number. If it was calculator active, you can type it in. All right. We did not get to these problems here. So the homework assignment is from the textbook. It is this right here. I was going to have you do those few slides after that as well as homework problems, but we didn't get to the questions like that, so we'll do that at the beginning of the class on Monday. So just do the book work. You should be in decent shape to do the stuff from the book. It doesn't have any like word problems there. Was there anybody that did not locate their book when we switched around? Everybody found them, hopefully.